from now on recorded. And the other thing is that it would be nice if it's possible for you to keep the video on. I mean, if you need to go leave and go do something, that's fine. But if you can have your video on, it's a better feeling for me that I'm talking to people rather than names. And the third thing is that I know some of the people here, and that's fun. There's some of the people I don't know. I'm not sure I know very well what people's interests and backgrounds are. So if I say something that doesn't make sense, then interrupt me and we'll talk about that. And if we don't get to talk about all the things I propose, no harm done. It's better to have a conversation that's meaningful than to say a lot of words that are useless. So help me out with that. And yeah, I think that's all the organizational things. So again, interrupt me when I make no sense. And I have to apologize. I'm going to say some things. Well, there are going to be some things that I'm just going to say. And if you ask me to explain them, then I'll say more words. But that's the way, in some sense, that's a limitation of what we're doing. So to those who I haven't met, hi, I'm Ronen. I taught some classes at DKU this spring, and I might teach again next spring, depending on who knows what next spring is going to be like. And my professional work is in string theory. And when I was asked to talk to this math club, I suggested that I would tell you a story about an intersection between math and physics that I had the good fortune to be personally involved in, so I know some of the history. And I think it's a really cool story. And so if you're up for that, I'm going to tell you a story. And as I said, if anybody has any questions or complaints about any of this at any point, let me know. So, and I'm going to use a whiteboard on my little iPad while we're talking so that I can scribble things. And so the story I'm going to tell you takes us back, or starts in the 1980s. So a long, long time ago. And we're going to talk about the thoughts of people working on string theory. So I'm not going to tell you all about string theory. But in string theory, one discusses the idea of what physics would look like if instead of particles, everything was made of little loops of string. And we like string theory because it offers a possibility, maybe, of being consistent. So here's my Blackboard technology. So string theory might produce a consistent quantum theory of gravity. That's why we like it. And we don't know what string theory is enough to answer the question whether or not it actually does this, but it's very promising. And in particular, what that means is that at some level, because that's the way physics theories work, when you understand relativity, you don't throw Newton out the window. You realize that Newtonian mechanics is valid at small velocities when things are not moving close to the speed of light. And when you introduce quantum mechanics, you don't throw Newton out and Einstein out the window. You realize that those calculations are valid in some limit where energies or momenta are large compared to Planck's constant. And so in some limit, this needs to produce, and it does, Einstein's GR. So the general theory of relativity is contained within and then extended by string theory into something that makes quantum mechanical sense, but there's a classical limit where you get GR. And in particular, it gives you a way, as a theory of gravity, of discussing deformations. You have gravitational fields in the spaces in which strings propagate, and these gravitational fields are at some level encoded in the shape of space-time and the geometry. And so this picture that we learned from Einstein about the geometry of space-time describing string propagation is inherited into string theory, and it's an approximate description. And so we do get from this conclusion from Einstein that the geometry of space-time, I don't know, yeah, this is sort of legible. The geometry of space-time determines physics. And this interaction between geometry and physics is the story I want to be telling today, or is at the center of the story. And so I need to say a little bit about what we mean by geometry in this context. So what is geometry? We all learned Euclidean geometry, and that's not the story I want to talk about. The kind of geometry, in technical terms, we mostly end up talking about Riemannian or actually algebraic geometry. And I'm not going to introduce either of those topics in detail, but the basic idea is that we want to discuss the shape of space. And how do you discuss the shape of a space-time or of a space? And there are mathematical formulations, and Riemannian geometry is the sort of best known of those, that describe, that tell us how mathematically to describe the shape of something. And the object that you use to describe it is called a metric. It's a measure, roughly, of how far different points on the space are from each other. And in particular, it contains the information of which points are very close to each other. So it tells you sort of the shape of the thing. But it does more than that. It also tells you how distance depends, changes, how the distances change between different points. And so the metric, which is what I will encounter under geometry. So geometry in Einsteinian or Riemannian theories is encoded in something called a metric. And the metric is something that allows you to distinguish, for example, between, everybody's favorite two-dimensional space, the surface of a sphere, like the surface of Earth, which is very nice and perfectly round, and a very closely related surface, but one which has a little bump here. So if you raise a big mountain on Earth, you can describe that as a change in the metric. So there's some mathematical parameters that you dial, and as you change them, they include the fact that, say, this point is farther from this point than it was before, right? So the distances between points around here change when you raise this mountain on top of Earth. So there is, as you would imagine, the metric is described by sort of a collection of functions with numerical values, if you want, on the sphere. And there's a large number of such possible functions. So there's an infinite dimensional space of metrics. Geometry can be described at various levels of refinement, and sort of the underlying, there are some properties that are shared between a sphere with mountains and a sphere without mountains. And in fact, a sphere, no matter how you distort it, anything that you can sort of below geometry at a rougher level of detail lies a field of mathematics that we'll also encounter, which is called topology. And topology is the description of those properties of a space that only really depend on which points are infinitesimally close to each other, which points are right on top of each other. And the thing about that is that when I raise this mountain, this great big space mountain on top of Earth, I changed which points, I changed the distances between points, but if points that were very close to each other remained very close to each other. Very tiny bits of Earth didn't change. This is a change which you can sort of continuously do, and I have to emphasize that when I'm talking about Earth or a sphere here, I'm not talking about the actual Earth, the ball, I'm only talking about the surface, the two-dimensional, if you want, the balloon that wraps Earth. There we go. We have advertising. I like it. Okay. So what is the kind of information that topology encounters? Well, topological information, as I said, is topologically, Earth with a mountain or with 7 mountains or without mountains is the same thing. What is not the same as Earth? Well, something of a different dimension, one-dimensional object. So dimension, if you want, the dimension of something. A little loop like this is not topologically the same as a two-sphere because they have different dimensions. But even if you maintain the dimension, there can be properties of the object that are distinct, and the famous example of something that is not the same, and I'll come back to this example many times, as a two-sphere. So remember, we're talking about a two-dimensional space, and a two-dimensional space that is not the same as a two-sphere is, and I used to know how to draw this, so let me see if I can still do this, the surface of a donut. This is meant to close here. And so this is called a torus. It's the surface of a donut or a bagel. And how do I know that this thing on the right is not topologically the same as the thing on the left? This is an interesting question. Intuitively, it's clear the one on the right has a hole in the middle of it. The sphere has no holes. But one of the cool things about when people study topology, they try to quantify this. They try to explain. How do you know by looking at a shape that it's topologically distinct from another shape? Well, what you want to do is describe properties of a shape that cannot be changed by making little wiggles on it. The study of topology boils down to the study of what we call invariants. An invariant is a mathematical property, often a number. Then it's called an enumerative invariant. You can count something, and the count can be different. The thing is an invariant if whatever it is that you're measuring does not change when you make small changes to the metric or to the shape. What's an example of an invariant thing that you can measure? Well, it's a property of a sphere, for example, of this object on the left, that if you draw on the sphere any loop, any closed loop, any little circle on the surface of the Earth here, a big circle or a small circle, then you can shrink it. You can make it smaller and smaller and smaller and smaller and smaller until it's a point, right? So I can shrink this sphere, the circle down, smaller and smaller, and then I can pull it off. The technical term for this theorem is you can't lasso a sphere, right? It doesn't have anything to hold on to and you fall off. On the other hand, if you think about the surface of a bagel, and again, I'm talking, I insist, I'm talking about the two-dimensional surface. And I'm going to say several things about this two-dimensional surface in a moment. Then it's clear that if I run a rope around this circle, remember that I'm only talking about the two-dimensional surface. So I can wiggle this rope around till it's here, and I can wiggle it so that it runs like this, but it stays looped around. Without ripping the rope, I can't pull it off. We say that the sphere is simply connected, the torus is not simply connected. These simply connectedness is a simple example of a topological invariant, and these are not topologically the same space. Okay, so that's this one thing I wanted to mention. I can say more things about a torus, maybe I will later. So popping that stack back, where does this tie into string theory? So, and where does topology come into it? Well, so the story that we know in the 80s about string theory is that we have one of the properties of string theory is that the consistency, the internal consistency of the theory suggests that if you want a featureless, uniform, homogeneous, isotropic space, like the space, to a good approximation, in which we live, like the space that Newton envisioned, which is infinite and featureless, then your space has the unfortunate property that space-time is 10-dimensional. And this is unfortunate because we all know that space-time is 4-dimensional. We live in 3 dimensions. So string theorists are trying to understand in the 80s what the relation is between the prediction of string theory and reality. And the notion they come up with is, wait a minute, we have a theory that describes, among other things, the shape of space. So we can discuss spaces of interesting shapes. And in particular, they come up with the idea of compactification. So what's the idea of a compactification? The idea of string compactification is that you describe the space in which we live, or space-time if you want to be fancy, as something like a product. What is a product? So let me remind you that I can think of the plane. So the idea in compactification, let me write the answer and then I'll say, is that your 10-dimensional space-time is given in the form of a 4-dimensional space-time that we know, the one we know and like, that is uniform and homogeneous and featureless. It's called Minkowski space, times some 6-dimensional compact space, which I'll call K, and sometimes call X and maybe M. It'll change its name as we go along. So what does this product mean? Well, let me remind you that when we think about a plane, we all learned about the Euclidean plane. It's got an x-axis and a y-axis. And every point here is described by giving its x and y coordinates. And you give me 2 numbers and I'll give you a point in the plane. I can think of the plane as given by a collection, if you want, of real lines. Imagine that you take the x-axis. The x-axis is a real line, and it is a 1-dimensional space. And the type of space that I said we lived in was called Minkowski space. And Minkowski space is a relativistic version of a featureless, uniform, homogeneous, isotropic space. It reminds us that in relativity, there's a distinction between time directions and the space direction. But for the purposes of this talk, Minkowski space is the same as Euclidean space. We're not going to imagine just a 4-dimensional extension of the Euclidean plane. Everything is the same everywhere, and all directions are the same. So what I'm going to do, the way I want to suggest that we think about the Euclidean plane is you can think of a 1-dimensional space, the x-axis, and you can imagine a collection of x-axes. And you have lots of them. To build the plane, you have to imagine that you have a whole y-axis worth of x-axes. So at every point on the y-axis, you insert an entire real line. Okay, this is the picture of this is the picture that describes the Euclidean plane, which we call R2, as the product of 2 real lines. You have a real line, and at each point on the real line, you insert an entire real line. That's what I mean by a product. And then how does that work in our case? Well, I want to imagine that K is compact. So and again, all my drawings will be 2-dimensional because I can barely draw 2 dimensions. So, and a picture of a more interesting 2-dimensional space is you can take something that is the real line times a circle. What do you get if you take the real line times a circle? Well, you take a real line, and at every point along it, you put a circle. So you get a real line's worth of circles. And what that looks like is an infinite cylinder, right? So I take a line, and at every point along the line, I insert a circle. And I get a 2-dimensional space that looks like a cylinder or a garden hose. So erase this guy in the center. Oops.
Why do the circles have to be aligned?
They don't. Well, so now you're asking about detailed questions. I can draw the circles in different ways, and I can describe different metrics, but at least at a rough level, when I say, it now depends what exactly the sense is in which I have a product. If I have a product metric, then that means I'm aligning them. Good question. Thank you. Okay, so what are the physicists basically telling us? They're telling us that our universe has four directions that look like this one, four of these, so this becomes four-dimensional space-time that we know and love, in which all you can move up and down and everything is the same, times six directions that are more like the circle. And the idea is that if you make this circle very small, smaller than the smallest distance we've measured in our accelerators, then you will never notice that it exists there. You will never notice that you can move in that direction, because before you've gone any measurable distance, you're back where you started. So the idea is that K is very small. And that explains why we measure things moving around in 3 dimensions rather than in 9. Okay, this is the picture. That's the picture of compactification. What it means is that when you say you are at a particular point in space, that's like describing where you are along this direction, and you've failed to give 6 more numbers that describe where you are on these, imagine, 6 tiny circles. But because they're so tiny, these numbers go from 0 to 0. So it doesn't matter. You can't go very far. So, you and I are at very different places in the 3-dimensional space. We might also be at different points in the 6-dimensional internal space, but since those numbers go from 0 to 10 to the minus 19 meters, it really doesn't matter. It's the distance in 3 dimensions that separates us. Okay? So this is the picture of compactification. Questions on that? Yeah.
So what do we need those like 6 dimensions for? Like, what does it measure?
So that's a good question. What we need them for is that it turns out that when you study quantum theory of a universe made up of relativistic strings, and I put in all those crazy technical words along the way, then you discover that it's either a very attractive feature or a very unattractive feature, but that most theories you write that contain strings are quantum mechanically inconsistent. They suffer from something called an anomaly in one of their symmetries, and they cannot describe a consistent, they're mathematically inconsistent internally. Let alone, I don't know if any of them describes our universe, but they're just wrong. And it turns out that to make these theories consistent, well, you need to satisfy some condition. And if you look at theories which have the form of string propagation in a featureless space, I insist on a featureless, uniform, homogeneous space, then again, there's one of these integers that you have to count, and it has to add up. The integer ends up counting the dimensions in which the number of perpendicular directions in which a string can wiggle. And it turns out the string has to be able to wiggle in 10 directions, which means space-time is 10-dimensional. Or if you want to be more careful, the string has to be able to wiggle in 8 space directions perpendicular to its own, to the string itself. So you end up with a 9-dimensional space. And now there may be other ways to write theories that are consistent, but if they have a description in terms of strings propagating in a space that is either featureless or at the very small size of a string approximately featureless, then that space is 10-dimensional. So a geometric approach requires 10-dimensional space-time. It's part of the properties of string theory. And the nature of that anomaly is not something I'm going to discuss very carefully here, but it's one of these calculations you have to do. It's one of the things I said, one of the things I promised that I would not explain. So here's one, but you want 10 dimensions. So string theorists are led, now in principle, you can describe string theory on any space because it's a theory of gravity. It can describe all the gravitational radiation, and part of the gravitational radiation, part of the fluctuations that string theory describes is the shape of these 6 internal dimensions, if you want. However, you imagine that gravitational waves are not so cataclysmic as to change the topology. So, right, you don't rip space in shreds unless you make something very singular. And so you can imagine that for example, that this garden hose universe that I'm describing here could have a gravitational wave in it in which the circles here are bigger and the circles here are smaller, right? Now, if that happens, this is something happening in the universe because it means that in terms of the space that we know, which remember goes from left to right, this part of space will behave differently than this part of space. So this is not a uniform one-dimensional space anymore, right? So physicists studying space would say, oh, this part of space is different from that part of space. This homogeneous version, where k is the same at every point of M, is the only way to make M4 homogeneous, make every point in space the same as every other point. So that's our starting point. And now we have an interest in a particular kind of spaces, because remember, we're doing a theory of general relativity at the end of the day. And so we want spaces of this kind that have a metric on them, this distance function, that is a possible solution of Einstein's equation. So we want to imagine our space with nothing in it. Of course, that's not the space we live in. We're in it. But to a good approximation, your first simple solution is a vacuum. And then on that, you can do perturbations like galaxies or people or whatever, particles. And so if you want a vacuum solution, then this whole space has to have a metric that is Einstein, that solves Einstein's equation. So there has to be a solution to Einstein's equation. This is the Einstein equation that if you took one of my astronomy courses, you saw me write down, I wrote down this equation maybe. And exactly what it means is not too important. And here was some 8 pi g over c squared t. And the right-hand side talks about energy and momentum. And so we're talking about a vacuum. So I'm going to put 0 here. And then it turns out that when you put 0 on the right-hand side, and the left-hand side is a measure of the curvature of space. It's something called the Ricci scalar and the Ricci tensor. And it turns out that if one is 0, then the other is 0. So when the right hand is 0, in fact, both terms are separately 0. So we're talking about Einstein's equation in vacuum is a vanishing identically of the Ricci tensor, which doesn't mean that the space is completely flat. It means that its curvature satisfies very special properties. An example of a solution to this equation in 4 dimensions is the gravitational solution of a black hole. So what we know as a black hole is the outside of a black hole. So it's a space with vacuum in it. So that just shows you that it's not trivial. Okay, so physicists are now in the 80s in the following interesting situation. All possible worlds described by this kind of string theory are described by all possible Ricci flat 6-dimensional compact spaces. Right? And now, what do I mean described? So let me explain a little bit what I mean by described. So what happens if you have strings propagating in a space like this? And again, I'm going to import some knowledge from string theory. In a compactified space-time like this kind of a space, there are going to be string, the kind of, remember that we're talking about string theory, but really strings are very small. What we detect is particles. Why? Because strings are so small, we can't see the size of them. But different wiggle modes of the string, different harmonics of the string could correspond to different particles. This is kind of the yoga of string theory. Now, in the context of such a theory, it turns out that the following thing is true. And this is, again, a good story to tell. In the context of a theory like this, the following fun thing is true. Most of the ways strings can wiggle. So we understand string propagation in the flat space, that we understand. But it's the wiggles along K that are interesting. Why is that? Because a certain form of wiggling along K will correspond to a certain kind of particle excitation that we see propagating around, moving around in M. Of course, if you have a solution for some string wiggling and standing still, then by relativity, I could just view it as a moving observer and I'll see the same particle moving. So we understand that part, relativity works. So you ask, but most of the ways that a string can wiggle in K will turn out, because K is very small, to have a large mass. And we won't detect them in our accelerators. We want the particles with very low masses. And in fact, as a good start, let's describe the particles with zero mass. That already turns out to be rich enough. Because you can arrange things, if k is small enough, that the first non-zero mass is way above the energies we can detect in our accelerators. So we look for all the massless particles. And then you discover something really cool. And the something really cool is that massless particles, in a compactification scenario, massless particles are associated to something very cute. They're associated, you get one massless particle for each solution to some kind of wave equation, what we call harmonic solution, on K. And now, what? You say, well, remember K is a compact space. It's like a circle. It doesn't go off to infinity. And when you studied waves on strings with boundaries at the end of them, or organ pipes with an open end and a closed end, you discovered that the frequencies or the wavelengths of the waves, sound waves you could create in such things were discrete. And I'm talking about not the spacing of these levels will be very large if the string is very short. So I'm talking about only the fundamental mode, the lowest mode of all of these, each of these oscillations. So of all the resonances that wiggles of K can have, I'm looking at the lowest ones, the harmonic ones, the actual solutions to the wave equation. And the cool thing is that for a compact space like this, it turns out that there's a finite number. And not only is it a finite number, so now we get the fun idea. So you look at, given some K, then solutions to, and there's different wave equations because of the ways that different kinds of excitations of the string interact with the curvature of the space. So there's modifications. It's not exactly the wave equation that we write down, not d squared by dx squared plus beta. There's some modification, but it's not that big. It's just fundamentally the same idea. And solutions to the wave equation, the number of solutions to the wave equation, to wave equations, I should say, and that implies massless particles. So look, a kind of the number of kinds of massless particles in 4 dimensions. Now, hey, I know something about the number of solutions to wave equations. What do I know about the number of solutions to wave equations? Well, the first thing I know is it's a number. It's an integer. It can be 1, it can be 3, it can be 7. How does that integer change if I wiggle K around a little bit? Well, one of the beautiful things about things that count in integers is they can't continuously change. They can only jump. So if they are defined in some sensible way in terms of the geometry of K, then the only way they can continuously depend on the geometry of K is not to depend on the geometry of K. These numbers of solutions to the harmonic wave equation are topological invariants. So as you wiggle K around, you take this K or a K with a little mountain in it or a K with a little valley in it, you have the same answer. This is an example of a topological question. Does that make sense? And this is the point I wanted to make. So these numbers, integer numbers, is a good place to look for topological invariants because integer numbers can't change continuously. They can jump. You have to make sure you're doing careful counts. It's subtle, but that's the general idea. So these are invariants. Awesome. So now, all right, physicists, make a list of all of the possible spaces K. Remember, spaces K that we want are not just any spaces. We are looking for a compact, Ricci flat. So they have to have a solution to this equation, and most spaces will not have a solution to this equation. And there's some other technical details about the kinds of metrics that they admit that come from the nature of the precise kind of stringy excitations that we allow. So I'll put the data down. We look for K to be a complex space, so it has a complex structure. What does that mean? Yeah.
Oh, so by the way, by compact, we mean like the compact in analysis, like
Yes,
terms?
precisely. But it's compact in analysis, which because we have a metric space, it's a very simple statement. It roughly boils down to the fact that you can't go an infinite distance anywhere. You can't have divergent series. So if you can't go off to infinity, then Cauchy's theorem works. Exactly right. It's that compactness. Yes. And do you have another question? Or that was the one? Okay, so it's going to be complex, which means, well, if it's an even dimension, then I can combine the coordinates into x plus iy and call them z. And the idea is that what is holomorphic function is a well-defined thing. So I can define well-defined analytic functions. I can do complex geometry on this. And if you don't like complex numbers, leave it. And in fact, it has to satisfy, the metric has to be adapted in some fancy way to this complex structure. It has to satisfy something called a Kähler condition. So all we have to do is classify all of the possible Ricci flat Kähler six-dimensional manifolds. And then each of them describes some kind of physical universe with some kinds of particles that are light, and then a bunch of heavy particles we've never seen. And in fact, it turns out that as we'll see, that the topology of K actually tells us something about the ways these particles interact, as well as which particles exist. And then make a catalog, compare it to experiment, and we'll know the answer. And this is what physicists are saying in the 80s. We're going to build a catalog of all these spaces. We're going to compare it to reality, and we'll know the answer to the universe. We'll have the answer. One quick question. Are there any such objects? Or is this complete baloney? And interestingly, well, first of all, yes, there are such objects. Trivially and easily, our little donut is actually an example of a two-dimensional space that is flat. It doesn't look flat, but it is flat, and has a complex scalar, everything you want structure. And the way to think of a donut and realize that it is flat is an important trick, so I'm going to teach you. A donut doesn't look flat because I'm thinking of it as sitting inside three-dimensional space, but that's a mistake. Remember, I wanted the two-dimensional space. So here's another way to think about a donut, which makes something very important clear. I can build a donut by taking the following thing. I'm going to take a square in the plane, or a rectangle if you want. And then, yeah, I'm going to roll it up. So I'm going to roll it up by gluing, and we have a notation for this. I'm going to glue this side to that side. So that means that if you wander on this thing and you come off of here, you come back here. That's a continuous line on this donut. So now I've made a cylinder, right? What I've built so far is I've built a cylinder. There, II is showing us a cylinder. Now I'm going to do it again. And I'm going to tie the top part of the cylinder to the bottom part of the cylinder. So that now this line that I drew here that was continuing here is going to actually continue here. So now this is a closed loop running around my donut. This makes several things obvious that are not obvious on the left. In particular, remember that I drew this circle here. I need to draw it here in some other color, so I'll draw it black. This circle here was a circle that you couldn't contract and so on, and maybe you could represent that by that line here. Now that's a circle because it comes from the top and joins itself on the bottom. There's another way to draw a circle on this donut that you can't contract, which is this circle. Oh, God, I've drawn it also in yellow, I guess. This circle on the surface of the donut also can't be shrunk because you run into the hole. And it looks like they're very different, but when you draw them here, you see that they're completely the same. It's just a question of which way you put the two-dimensional donut into 3 dimensions. Lots of fun questions about geometry and topology here. But so such things exist. But what this shows me is that because I made this by identifying a piece of paper that was totally flat, it was a piece of the Euclidean plane of my iPad screen, which is flat. That gives me a metric on the torus that is flat. And if it's flat, it's of course Ricci flat, right? It's just identified with a piece of the plane. And yeah, so, but are there non-trivial? You can do the same thing in higher dimensions. You can take 6 circles. So I think of a torus. What this is showing me is that a torus is a circle of circles. That's what I just said. Take a circle, at every point on it, put a circle. Just like we built the plane, now you're building a donut. So of course I can take 6 circles. That's flat. And it is Ricci flat, and it's compact, and it's everything. But that's kind of a dumb solution. Can you do something more fancy? And the existence of such non-trivial objects was yeah, go ahead.
Sorry, I kind of missed the part. Like, how do you do 6 circles again?
See, you understand that a donut is a circle of circles? Take a circle, at every point on a circle, put a circle, and when you put them together, you get a donut. Okay, now imagine doing that 6 times. Just keep going. A circle of circles of circles of circles of circles of circles. You know, there's the famous joke about an engineer and a mathematician in a string theory talk. I have to tell it. And the string theorist is going on about 10-dimensional geometry, and the engineer looks at the mathematician and says, I don't understand. I can't follow this baloney. How do you, and the mathematician's sitting there all happy. And the engineer says, how do you think in 10 dimensions? And the mathematician says, it's very easy. First, I imagine a space in n dimensions, and then I set n equal to 10. So at some point you have to do some you have to abstract some things, but it does work. I mean, you can be precisely mathematical about that one. Okay, so the question of the existence of solutions to these conditions was actually an interesting question in mathematics for various reasons. In the 70s, there was a conjecture and some useful information about such metrics, should they exist. Remember that Einstein's equation is a nonlinear partial differential equation for the metric. And it's nonlinear because it's, partial because we're in multiple dimensions. It's nonlinear because gravity gravitates. And so it's a complicated differential equation, and proving the existence of solutions is a big deal. But there was a conjecture that these equations had solutions, and the conjecture was due to a mathematician called Eugenio Calabi. And he conjectured that such solutions would exist. And then in a tour de force of analysis in, I think, 81, a mathematician called, well, in America, he's called Xingtong Yao, proved it. So he proved Calabi's conjecture, and these spaces that have solutions to these equations are called Calabi-Yau manifolds. So it was very heartening that when physicists discovered that these would be the solutions to string theory, they could happily refer to Yao's proof of Calabi's conjecture and say, aha, these things exist. And furthermore, there's a strongly supported conjecture that there's a finite number of them. What is number? There's a finite number of topological classes. Of course, on each of them, I can deform the metric a little bit, but there's a finite number of topological classes of Calabi-Yau manifolds. And now you have to list them. Each of them will give you a particular universe. Find the one that describes our world, and you're done. Okay? Now, how does a Calabi-Yau describe our world? Well, so suppose you have a K. What I said is I want to look at solutions to the harmonic wave equations of the right kind on K. And it turns out that a particular, here's what we learn from K. There are particular topological invariants, so numerical counts that determine something. And there's one of them called H11. It's somewhat similar to a Betty number, and it's a count of it's a counting of the number of a certain kind of solutions to a certain kind of wave equation on K. And this, in the context of both, remember that I'm thinking about, I haven't given a topological space. I have this huge infinite dimensional space of metrics. We said I can put various wiggles on it. Most of these wiggles will ruin Ricci flatness. It turns out that if you insist on solution, changing the metric, but keeping it a solution to Einstein's equation, well, that's a finite dimensional space of such metrics. You can only deform the metric in a very limited way. If you wiggle it here, you have to unwiggle it there because you're trying to find a solution. So the space of solutions to something like that is called the moduli space, and you get a moduli space of Einstein metrics on this Calabi-Yau manifold. And there's this number H11, and there's another number called H21. And each of them counts the following thing, counts different things. So first, the total number of massless particles in the physical spectrum of some particular kind is actually determined by the sum of these numbers. So the total number of massless particles is this H11 plus H21. So I have, I don't know how to say it, massless particles, you have the sum of these guys, but they behave somewhat differently. That you can classify sort of, there's a certain kind of particles of which you have H11 types and a different kind of particles of which you have H21 types. Okay. H11, the other thing that is classified, and the reason that these are related to give the same number is either because you're dealing with very special geometry from a math point of view, or it's because you're dealing with very supersymmetric theories from a physics point of view. And the end result is that the dimension of the space, the number of different ways you can wiggle the metric, is also counted by H11 and H21. And in fact, they count sort of slightly different kinds of deformations. H11 is the dimension of the space that you get by sort of changing the size of the space in different ways. It's the analog of, if I take, well, I'll try to be a little bit more precise, and H21 counts the ways to deform the shape of this object. And so there's an H21 dimensional space of changing the shape and an H11 dimensional way of changing different sizes. And that together gives you the dimension of the space of the ways you can deform this metric. Okay. And also to each of these ways of deforming is associated a particle. So there's a massless particle of this kind that I'll call, I don't know, there's various names to call it. These are typically called, well, okay, I'll call these TC type particles and these C particles, and they have different, slightly distinguishable physical properties, but they can be related. Let me see, somebody asked a question, but I didn't see it. It went by too fast. It's sort of degrees of freedom of solutions to a particular equation. So this moduli space that I'm counting is the dimension of the space of the ways I can deform the metric, preserving the Calabi-Yau, the Ricci flat solution, the Einstein equation. Okay. And so again, picking a topology, and one can ask, what are the values of these numbers? These are positive numbers, of course, H11 and H21, they count something. And typically, it's very easy to make examples. And the first examples that people make, H21 can be very large, H11 tends to be quite small. And now, in the 80s, physicists realized that you can actually use geometry to make approximate calculations of some properties of these particles. And the particles, so I'll call the size parameters here, I guess S. So, oops, no. I'll call these size parameters S, and there you can label them, right? S1 up to SH11, because there's that many numbers that it takes to specify the shape of something, and the size, and then I'll call the shape parameters. Oh, I'm really bad, aren't I? Size and shape both begin with S. I didn't realize that. So I'll call these guys, oh, I don't know, T1 up to TH21. Okay? And now, so these are the physics that is described by this particular K6. Well, there's a family of different physical theories, and they differ. As I modify the size and shape, the physics changes. What changes? Well, the number of particles of each type doesn't change, but the way they interact changes. And I can make some calculations about the way they interact. And again, these interactions are constrained by the symmetries of the problem. And it turns out that the most easily calculable part of these interactions is some kind of amplitude or a probability for an interaction between three particles in some sense of either the TC kind or the C kind. And so you get some amplitude, and they turn out to have mathematical descriptions. So for the coupling of these, you get something like a C cubed correlation function. It's some physical property you can calculate. And the idea is that to each of these particles, remember, I can associate one particular solution to the wave equation. And basically, the intersection is an integral over K of the product. So this is of C1 times C2 times C3, suitably arranged. I take these functions that are solutions to the wave equation, I multiply them, and I do an integral over the whole space. So I get a number. And that number measures the strength of the interaction between these particles. And this number turns out to have a very interesting thing. This is a function, is a function of these T. So these T's are, I forgot to say, complex, naturally complex numbers. And this, I'll call it C cubed, is a function of T. And in fact, it's a holomorphic function of these H21T coordinates. And its dependence on the size coordinates is even nicer because it doesn't depend on them at all. And conversely, we can compute the analogous thing, kind of interaction for these TC guys cubed. And this too has a form that looks like an integral over K of sort of TC1 times some product of things, roughly. That turns out to be a topological invariant. That's some kind of intersection number. This is just a number. It doesn't depend on anything. But this turns out to have an infinite set of corrections that look like e to the minus s. So they become very small when S become large, when the size of the space is large and curvature is diluted. And there's sort of S dot n, different combinations of S, exponential suppression. And then there's some calculation which is not exactly an integral, but it's like an integral. It's a different topological invariant of the space K. So now, that's great. The space K has an infinite set of topological invariants that I haven't described exactly. I can tell you something about them. And when you sum them up, you get this correlation function, and you weight them, you get this. So this is, of course, a function. TC cubed is a function of S, and it's suitably defined. It has some holomorphic dependent on S. And its dependence on T is even nicer because it doesn't depend on T whatsoever. It's like two completely separate systems. Okay? Now, in the 80s, physicists looking at this are very bothered by this. They're bothered aesthetically because it looks like the distinction, which kind of particle you associate to the red family and which to the blue family, you could sort of make a change in the way you think about the theory and flip them. But on the other hand, remember that to physicists, this limit when S is very large and curvatures are diluted, this is the simple limit. This is the limit where the curvatures are diluted. The physicists call this the weakly interacting theory. It's almost free. Space is almost like flat space, like 10-dimensional flat space. And so physicists at first thought that this was the answer, and then they discovered this whole crazy set of corrections, and they were bothered. Why would the TC particles be so unfortunate as to have all these corrections, but the C particles be given exactly by the free field calculation when I could have actually relabeled them? I could just think of, re-identify things differently. And so some physicists had the crazy idea, what if there were a different space, which they would call, I'm going to be nasty, I'm going to call it a backward K. And backward K would have the property that it would have as many size parameters, as many solutions on backwards K to this kind of wave equation as there are to the other kind of wave equation on K. In other words, these two spaces would satisfy H11 of backward K is the same as H21 of K. Yeah. Scientists try to be inventive. That's why we all know Greek, right? And H21 of backwards K would be H11 of K. Right? And then you could imagine that there would be two different geometries that describe the same physics. You could describe the same physical theory as either a universe M cross K with one identification of particles, or M cross backwards K with different identification of particles. Notice this would be a completely revolutionary idea because it would mean, since they specify the same physics, that physically they're the same. That means that in physics, in string physics at least, the topology of space is an ambiguous concept. Of course, these are topologically distinct. They have different values for topological invariants. So you can't, they're not like one has a wiggle and one doesn't have a wiggle. They're completely different. You have to rip them apart to make them the same. And yet they give the same physics. Okay, so some physicists said that. Everybody ignored them, of course, because this is not happening. And besides, remember, all of the examples that we knew how to build had arbitrarily large H21, but very small H11. So you couldn't imagine building theories that had them reversed. Okay? Now, and then the story gets fun because then in about 87 or 88, for various reasons, a postdoc named Brian Greene and as a graduate student, me, we're looking at the particular kind of solutions that had been invented by a physicist called Doron Gepner, a set of physical theories where it was conjectured that they would describe one of these kinds of models at a particular point. So particular values of S that were not infinity and particular values of T that were not infinity. And we were looking at to see there, and there you could calculate all of these correlation functions exactly. So Gepner made this revolutionary, had this revolutionary idea. We were trying to understand its implications and what we could do with it. And playing around, we discovered, literally playing around, trying to solve something, we realized that there's a modification you could make to one of Gepner's theories that when you run it through the machine of doing the calculation, looks like you started with a particular point in the space of all k's, and you ended up with a particular point in the space of all backward k's. And we were floored. And first we thought there was an error. We had just, remember there was a choice you had to make to decide which kind of particle. So we thought, we accidentally flipped the choice. but we systematized it, and eventually we came up with the fact that a proof that in fact, for a certain class at least of Calabi-Yau spaces, you started with one, I could give you another that had exactly the same physics. And we called those pairs mirror manifolds because there was some reflection, because they came in pairs and there was some reflection on the list of numbers and the way you wrote them down. So two mirror space manifolds, so here's the idea, K and K have the property that they're topologically distinct spaces. They're completely different. But physics on M4 cross K is exactly the same as physics on M4 cross backwards K. In particular, remember there's a family of each of these guys. And so there would be a family of Ks described by S and T. Right? And you pick a value for all of these numbers and you get a particular one and you can describe the properties of that physics. All backwards Ks are also described by S and Ts, but you have to remember, I'm going to write it sort of weird, there's, I'll call them S hat and T hat. And the reason I'm using backwards colors is because there's as many red ones, the counting is the same. There's H11 of these, H11 of K, and there's H21 of K of these, but that's equal to H11 of backwards K, so that's how many there are of these, and that's equal to H21 of backwards K of these. So describing the
I
shape,
have a question.
yeah. It's a mapping on the space of, on a set of families of Ks. It's not a bijection on the space itself. There's no local map from points in K to points in K hat because they're topologically distinct.
Okay.
You can map a point in one to a point in the other, but indeed it is an injection. It is an involution of the set of spaces. Okay. But it's not a bijective mapping at all. There is no map. There's no continuous map from one to the other because they're topologically distinct. Okay. So when you map one to the other, you have to do violence. So we can't map points in one to point in the other, points in the other. But solutions to the wave equation on one are equal to solutions of a different wave equation on the other.
Okay, I understand.
And furthermore, and now the idea that they're the same physics is that I can map a particular K is equal as physically to a particular backwards K. So that I can find S hat of T and T hat of S, such that if I set the S hats to that function, then I get exact equality. This is called the mirror map. This is the set of, you want to describe K at a particular size, that determines what shape of backwards K. You want to describe K at a particular shape, that tells you what sizes to assign to the bits of backwards K. And if you manage to figure out how to map one thing into the other, then you would tell me which backwards K exactly corresponds to the identical physics as K. Now, why is that important? That's important because then you could compute this object that I called, say, C cubed of K, which remember was an integral on K of C1, C2, C3, and was a function of these S variables, then independent of the T variables. But this would then supposedly be equal, because it's the identical physics, to the calculation of a T hat cube type thing on K, on backwards K, and that would have, remember, had the description as an integral on backwards K, integral on backwards K of some TC1, TC2, TC3, which is just a number, plus this infinite number of e to the minus S hat, I think, was the size, guys, yeah. Yes, S hat. Did I do it wrong? Shaped up. Yeah, T hat, whatever it is. Okay, T hat, yes. E to the minus T hat times some n of some other integral, these other new invariants that I didn't quite describe. So, hey, wait a minute. The deal is, and okay, so this was the idea, and we were excited because it meant you could actually, these calculations are easy to do. This is an infinite number. The right-hand side is an infinite number of integrals. Just do the integrals once on the mirror manifold, and you'd get all of them. We thought, we'll solve the string theory. Turns out that, of course, mathematicians had a different way to interpret the same kind of calculation. To them, the interesting object were these numbers. These suitably, in some sense, are integer numbers, just like these are. Integers, what does that tell you about them? They're invariants. They don't change when you make a deformation. The dependence on the t hats, which is the dependent on the s's, comes only from this prefactor. These numbers are t independent. They're invariants. They're called Gromov-Witten invariants of the manifold backwards k, whatever it is. The important thing about this is that there's a whole family of these topological properties of spaces that mathematicians, for various reasons, were interested in calculating. And they had done some calculations of the numbers for n equals 1 and n equals 2 in a simple example. And then in 1991, along came a bunch of 4 physicists and said, hey, we could use this mirror trick. They found the mirror manifold to the space that they were interested in. They figured out this mirror map. They computed this function. Then they expanded it in this basis once they had the mirror map. And what that gave them is essentially a generating function for all of the invariants that the mathematicians wanted. At order 1, at order 2, they ran it on a little computer and went to order 21 and got numbers with 17 digits and said, good enough. And this got mathematicians excited because if you could make this meant that this mirror thing might mean something. You can make mathematical calculations. You can check. Up to now, all I said was physics and mathematicians, none of it is proved. It's all path integrals. Nobody believed it. Now you had a number. So mathematicians got excited. And in fact, the first 2 numbers that they got agreed with the first 2 numbers mathematicians had gotten. The third number disagreed. There had been a really powerful pair of mathematicians that had done a very complicated calculation. In this particular example, got the third number, and it didn't agree with what the physicists had. And there was, in fact, in 1991, a conference in Berkeley where we all showed up, a bunch of mathematicians, a bunch of physicists, and we started talking. And I should point out that I was lucky enough, I was at Harvard. So when we came up with this idea of mirror symmetry, we went up to none other than Yao. He was across the hall. And we said, hey, Yao, we got this idea. You can find manifolds. And Yao said, this is baloney. That can't happen. You can't possibly find manifolds with big H11s. They can't exist. Okay, even Yao is wrong sometimes. It turns out there was a way to make them in special cases. We had this conference where, tout le monde showed up in Berkeley and we argued about how do you define these invariants, how we define these invariants, what does it all mean? And at the end of the summer, the pair of mathematicians who had done this heroic calculation found a bug in their code and they fixed it. And then it turned out the numbers the physicists had precisely were the right invariants. And a famous algebraic geometer circulated an email that we all preserve that says physics wins. And so the point is that by interpreting this geometric data as properties of a physical theory, you got insight into 2 spaces that are, from a mathematical point of view, completely unrelated, but whose mathematical properties are somehow encoding those of each other in a very, very non-trivial way. Remember, there's no map from points in K to points in backwards K. They're completely different spaces. But because They are related by some crazy property, relation that encodes the fact they are the same physics. Their geometry encodes that of each other, and the behavior of an integral as you deform the parameters of k gives you a generating function for all of the invariants you ever wanted at backwards k, and vice versa. So this became a very interesting object, both for mathematicians and for physicists, and you can learned a bunch of things since then. There's been many books written on this topic. Because you can learn geometry by applying physics, you can learn physics by applying geometry, and it's one of those cases where we got lucky and the interests of two communities overlapped. Understanding the nature of the relationship geometrically between k and backwards k is an ongoing subject, and it's far from closed. Many things are not known. Among them, one, do all Calabi-Yau manifolds have mirrors? Probably not, almost certainly not. But if not, then which do? We don't know. So not all Calabi-Yaus come in pairs. We can almost prove that. But all of the examples we can easily build have a mirror. One wonders, of course, can you construct? How do you go? Can you construct one from the other? And again, in examples, we do know how to do that. There are many other, how are the can you prove this mathematical relation more directly? I mean, without going through physics. So can you prove mirror symmetry? This relation between the invariants. The answer to this is partly. Some of it is done, including a work by Sasha Giventhal at Berkeley, and then an elaboration of that by Yau and collaborators. And there's an ongoing 10-year, multi-million-dollar collaboration to prove mirror symmetry, essentially. That's going on. So maybe someday we'll know the answer to this. And extracting physical consequences from this for the kinds of string theories we're interested in is still ongoing. So it's become a tool, right? It's something that we use whenever you have a problem. You can say, well, how does it look in the mirror? Maybe I can learn something about it. And there are many, many, many extensions and elaborations and whatever. So there's lots of open questions. There's lots of good things to understand. And this is a great story for me to tell because it's something that I almost stumbled into as a very young guy. I happened to have, the tools to make certain kinds of computations that turned out to be really lucky. So it was really fun. And I got to meet a whole bunch of people from various fields and educate each other on, oh, that's what you mean by conformal. No, this is not what a modulus is. We think of a modulus as that, and then try to figure out what you mean. So being on the middle in between disciplines is a fun place to go. And I'll stop there and see if you guys want to ask questions.
I had a question about H and what does H11 and H21 sort of represent? What does it mean a little bit if you could talk about that?
So these are integers and they count roughly, what they count is, as I said, you have some wave equations. Wave equations are fundamentally linear equations. You can superpose waves. So you can ask, when I said the number of solutions, I lied. I used uncareful terminology that physicists use. Of course, the space of solutions to a wave equation is, you can take a solution, you can multiply it by 2, you can add 2 solutions. It's what we call a vector space, and it has a dimension. So H11 is the dimension of the space of solutions to a particular kind of wave equation on this space, and H21 is the dimension of the space of a different kind of solutions to a different kind of wave equation. Now, the kind of wave equation is not too essential. So it's, and in particular, they're both positive integers. One way to say it, so what's an example of a of one of these numbers? I can try to put it this way. I'm trying to think of an example for which we would recognize. So one example of this is that, and I don't want to get in too much into Kähler, so I'm going to deal with simpler spaces. So for any space, I can have a number called H1, which is roughly the dimension of the space to the solutions of some kind of wave equation. But what that is equivalent to, what shows you that it's a topological invariant in an integer, is roughly the dimension of the space of non-contractible loops. So we can guess what H1 of a two-sphere is. What is the dimension of the space of non-contractible loops on a two-sphere? Nice round number. There are no non-contractible loops on a two-sphere because you can't lasso a sphere. You pull it off.
Okay.
So this says H1 equals 0. How about a donut? What is the dimension of the space of non-contractible loops on our donut? I'll draw it twice. Either this donut or that donut. Yeah, it's 2. Absolutely. There's this loop, there's that loop, and this loop. And of course, there are many other non-contractible loops, like this is a non-contractible loop. But it's in some sense the sum. You go around once one way as you go around the other way. Okay? So this is H1 equal 2. So are there more complicated, topologically different two-dimensional surfaces? It turns out that classifying, I should be careful, closed, compact, orientable, technical terms, two-dimensional surfaces is very, very simple. And H1, in fact, is good enough. If you know H1, you know the answer. And so what's an example of a surface that is not equivalent to either of these? Well, we can actually draw it. Yeah, you can do this guy. Like two donuts with a neck connecting them. That has two holes. Intuitively, it's pretty clear you can't make it by deforming into any of the others. Good, so question to you, what is H1 of this guy? Something to play around with in your head and think. Yeah. Very good. Yes, indeed. You are right. It is 4 in this case. Okay? Play around with it. And of course, you can now keep going, right? It's easy to imagine you can make a chain of such donuts. And it turns out that that's the most general thing. And if it has G holes, then H1 is 2G. And that's all that's all you get. And two spaces that have the same number of holes can be deformed into each other. Now this has to do with the fact that we're dealing with two-dimensional objects. If you were in higher dimensions, you could imagine that a higher dimensional object can have holes of various dimensions. So roughly H11 is a count of the two-dimensional holes in something of a certain kind. And H21 is the space of three-dimensional holes. Now I can't draw them. But the 2 and 3-dimensional holes in a 6-dimensional object are roughly H11 and H21. Okay, that's roughly what I'm talking. And the beautiful thing is that the number of holes is related to the number of the dimension of the space of solutions to a harmonic wave equation. This relation between analysis and topology is one of the most beautiful results in modern mathematics. Right? It tells you that you can solve the analysis problems and the answer is topology. Or you can solve topology problems by doing analysis. That's in math, that's an awesome result. That's really cool. Which is why harmonic solutions are so important and wave equations are so important, by the way.
Oh, so, well, I still don't understand how does one side of a mirror has corrections and one doesn't. So like, where does it in the
Well,
end come from?
corrections relative to what? That's a valid question. And it turns out that there is a limit in which the calculations simplify, in which physics reduces roughly to the physics of flat 10-dimensional space. And that limit is where the sizes of everything are large. So that's often infinity in one set of parameters. And then if you go to that limit in a suitable sense, then well, there's underlying all of this is some two-dimensional quantum field theory that lives on the string world sheet, and that becomes a free field theory. That's the technical sense I'm saying. And then this infinite set of corrections is a set of quantum contributions to the free field classical result that you obtain at infinite size. Now, a valid question is, wait, it's infinite size of one space, so it's some limit. What kind of limit, what kind of weird shape does the other one do? It has to be some special shape. So what is the shape that is the mirror of infinite size? That's an interesting question. It turns out it is a singular shape, and it's actually very non-trivial to find it, but we understand it in some sense. Yeah. So I don't know if that answers the question, but the idea is that as you make things bigger, curvature, if you remember, is naturally a thing that is measured in units of 1 over length. It's like a inverse radius of curvature. It's 1 over r squared, 1 over size squared. And so as you make everything bigger, the curvatures of things become small. The integrals of curvature over surfaces are constants. And so the curvatures become small, which means those curvatures are the deviation, measure the deviation of the physical theory from free fields, from the free propagation of strings without any interactions. That's one way to think about it. And so those exponential terms are corrections to the free field result, which we have a free field result for one and a free field result for the other. The free field result for one turns out to be exact. And the free field result for the other has an infinite number of corrections. And yet they're equal, which is the cool thing. They're equal between mirrors.
I have another question. So could you take a Mobius strip, which is a two-dimensional object in a three-dimensional space, and then find the H1 of that? Because if you describe a donut as a square rectangle that's folded.
Yeah, so that's a really good question. The answer is first, so a Möbius strip, depending on how you account it, all of my surfaces were closed and compact, so they had no boundary. And a Möbius strip has a boundary, right? Because it's a strip, or it's infinite, depending how you count, how you want to construct it. The other thing that the Möbius strip fails in my little classification is it's not orientable. So I said a little technical word at some point, is it closed? Orientable, and I snuck it in as a technical qualification, and you're onto it. Orientation means that I can assign if you want a sort of basis, an X and a Y basis, consistently in such a way that it's a right-handed basis everywhere, I can declare. And the property of a Möbius strip, of course, is that when you go around, you come back to the same point, you're flipped. You're on the other side of the paper, but as a two-dimensional space, it's the same thing, and inside has become out. So a Möbius strip is the basic example of a non-orientable space, and therefore is not in my classification. If you wanted a closed compact cousin of a Möbius strip, you'd get a Klein bottle, which is closed and compact, but has no inside. And unlike all of these guys, does not divide 3 space into 2 disjoint sets. And Klein bottle is a non-orientable 2-dimensional closed compact space. Non-orientability in particular means you can't make a complex manifold out of it. You can't consistently assign pairings x plus iy, because when you come back, you're going to get x minus iy. So z is going to be mapped to z bar, and that's not a holomorphic mapping. So from the point of view of a consistent complex structure implies orientability. And there are string theories that are adapted and can be defined on non-orientable spacetimes. We use that a lot. But for the purposes of today, everything was orientable and complex.
Okay, thank you.
Cool question. I have to say thanks to everybody for surviving so long. That was a really long talk. I had told me that we could go a little bit long, and I'm afraid I kind of stretched the limits of that. But I guess that it is.
No, it's fine. We have reading seminars. They're 3 hours long, so it's fine.
Yeah, I mean, I was going to say we did a Russian seminar. That's the standard. Yep. So, but I suspect that people are getting tired, so I don't want to drag it out too long. I should say that there are, I didn't get to talk about it, but there are actual ways that people have discussed. There was in certain examples, the way that Brian and I discovered, and then that was generalized hugely by a bunch of mathematicians. To some combinatorial dualities between the construction of K and the construction of backwards K. And then there is, based on, it's very interesting, but there is an idea that comes from deep math due to a deep mathematician called Maxim Kontsevich, who's has the property that he writes these amazing papers, and then a decade later, we all understand why he might have been right. And indeed, Maxim wrote some idea for how mirrors could be two mirror spaces could be related at some deep category theory level. And about a decade later, people had made all kinds of progress in string theory, and a string theoretic interpretation of what Kontsevich had said. This is called homological mirror symmetry. And it's what Yao and company are actually trying to prove, because it's a precise mathematical and provable statement. And we discovered that, in fact, a prediction of the identical physics would be formulated as Kontsevich's homological mirror symmetry. And the objects, these crazy categories he was constructing actually make sense in string theory, but we didn't know when he wrote them down. They mean something. And that in fact, at some level of detail, there's even an almost geometric construction that takes you from K to backwards K. It's at a spiritual level, it's pretty well understood. It was proposed based on string considerations by 2 physicists and a mathematician, or I guess 1.5 physicists and 1.5 mathematicians, because one of them was kind of in the middle. And the mathematician was Yao, and this is an explicit construction. The only problem is that it sort of describes how to start with K and end up with backwards K. And it's a recipe. The only problem is that it only works in a situation as written where neither of those spaces make sense. They're both very singular. And the question is how to deform it a little bit so we understand it where they're not totally singular, where we get actual geometry. And there's a lot of work on trying to figure that out, but it's far from done. So at the moment, we don't have any systematic way to actually start with K and construct backwards K. We have ways to start with the family K and construct the family backwards K and then figure out the mirror map, but that's indirect. Lots of work is still going to be done on this subject, so not finished. And I apologize for all the times I said, and then string theory says this. Some of this stuff is actually, I tried where I could to sort of motivate, but some of this stuff I can't actually do. Okay.
How do you start doing string theory though? Like, what do you have to know to like study it?
So there are many different people who do things that are, you could broadly account for as being part of the string effort. There are physicists, so a physicist who does string theory typically will start either by training as a particle physicist, mostly by training as a particle physicist, learning quantum field theory, and then extending it. Some people get there a different way by starting by studying relativity and the solutions to Einstein's equation and gravitational physics, and then meeting the particle theorists from the other direction. Mathematicians who work in string theory typically, at least in the old days, were typically people who were algebraic geometers. So there's a lot of application. Mirror symmetry in particular lives very well in the field of outside algebraic geometry. But more broadly, Yao is a differential geometer and an analyst, and so some important results have been, if people who like to actually work hard, do analysis. There has been work by topologists in this field. So there are lots of people who train in mathematics and come into the field from that direction. For a while, we had a sort of program at Duke. I think it kind of fell apart, but there's remnants of it, and there's a similar effort with different emphases going on at places like the University of Pennsylvania, for example, has a strong group in math and physics of people who are algebraic geometers mostly and particle physicists who work a lot together, and in particular have a combined sort of graduate training program. And the idea that we had, and that they also to some extent are implementing, is that if you're a student and as a graduate student you learn both quantum field theory and algebraic geometry, so that you have both of them as your first language and as mother tongues. They're in hardware, you don't have to emulate them. Things you learn after grad school you emulate. They're never hardware. But up to grad school, these are things that are embedded and you have a good intuition for them. The idea was to train a generation, and still is, of people who are deeply bilingual and who therefore will probably make progress where we got stuck, because we had to sort of meet up coming from different directions and sort of figure out how to translate. And so there are places where people are doing that intentionally in that field. But there's people doing string theory through a huge spectrum of specialties. There's lots of different projects. And at the moment, the field is sort of broadening, because it was very narrowly focused for a while. At any given time, we were all doing the same thing for about a couple of decades. there was always the problem. And when we gave up on this problem or made as much easy progress as we could, somebody would come up with a new the problem, and we'd all jump to that. And it was a very young field at the time, and now it's kind of more mature. There are many problems, and they're not going away very fast because nobody's solving them. And so different people work in different ways, and we don't know where breakthroughs are coming. You know, we're no longer in a period of the sort of rapid revolutionary growth where the whole field transforms every 3 years. So maybe that's a time not to do string theory, I should say. It was more fun back then. You know, it's like riding a Bronco, you could barely keep up with it. And you knew everybody in the field at any given time. You know, there were 300 people. So, worldwide, it was great.
By the way, people who have to go, like, I know for some of you, it's like, really like.
I'm avoiding work, so I'm fine. When I get done here, I can work. I'm happy to continue chatting, and I get to see people I haven't seen in a long time, so that's certainly cool.
Oh, so you only teach this second summer term?
At Duke, yeah, only the second summer term, yeah.
Oh, nice. So you have a bit of rest from noisy students.
It's, you know, there was a pretty intense end of spring, so I was ready for a couple of weeks off. It's exciting at the end there. And I get to prepare a little bit, but we'll see. We're now trying to decide, they're trying to decide whether they're going to teach on campus in the fall, and that's still an open question.
Oh. So like, is you guys doing better?
Better than what? Well, I think the thing that, yes, in a sense, yes, the number of new cases in the US and even in North Carolina is decreasing. I think in the US is decreasing slowly. In Carolina is increasing slowly. It depends exactly how you count it. But it's clear that we're often exponential. Okay, so for whatever that's worth, that's a good thing independently. But I think the problem is that nobody has a reasonable forecast of what September is going to be like. And so.
Oh, wait, actually, I forgot to ask. So like, remember we had this dilemma was like where to put the telescope, like where to go stargazing stuff with the telescope. And like, I think, and I asked a couple of professors if they know any like places near Kunshan. And actually one of the professors referenced me to you and said that you know some places near Kunshan where you can go. Because you were taking like students from DQU, it's like a couple of years ago there.
So where we went, it's a kind of a tricky thing. So there's several, when I was there in 2015, we went looking around for dark places. And what we found was, we didn't find a great place. There is, I forget what it's called, but to the west of Kunshan is this huge lake. Not the lake where all the crab restaurants are that's in Kunshan, but there's a huge lake, one over to the west. It's all lakes. I forget its name, I'm sorry. Mm-hmm. And in that lake is an island. And it is said that if you get to the island, then you get really nice dark skies, relatively, because you're far from all the lights. I have never been there, but I've heard it said that that's good. You could also imagine, of course, the ideal thing is to go up to Nanjing, to the Purple Mountain Observatory, which is up in the hills above Nanjing. And there they actually have good skies. So that's another option. I couldn't make that. I couldn't get Professor Andrew Field, who was our director at the time, to approve such travels at the time. What we actually physically did is, when I taught astronomy at DKU, we had a field trip which included a visit to the Shanghai Astronomical Observatory, which is on one of the tallest mountains in Shanghai district at 100 meters altitude, and which is very tall for Shanghai. And not far from it is a radio observatory. I think it might be Yangcheng, I think, is the lake we're talking about, but I'm not sure. I'll look it up and I'll tell you. There are, but I'm not sure. Now I have to look which ones. I remember both Tai and Yangcheng. I'll look. There's one close and one farther off west. And the bigger, farther off west is the one with the island. In any event, we went down to visit this radio observatory. And not far from there, we found a place which was basically a parking lot. And it was reasonably dark, and we put the telescope out there and did some observing. It was better than on campus, but it was far from dark skies. You know, you're too close to Shanghai, it's not gonna happen. You're not gonna get glorious skies. I think that is what I know. And someday I will come by and maybe have time and get someone with a car and be able to travel around and take a look. But by then, hopefully, there will be students. And the students, since we now have students who've been there a while, you all know exactly where the dark skies are. And so we'll do that.
We'll try to find some before you come. But yeah, I don't know how long it would take.
Yeah, that's what's pretty certain is that students will get there before I do. I think that's a good.
Now I need to get someone with a car.
That I might be able to help with. You know, there's faculty members who drive down there, so I might be able to sneak that in. But I mean, just for this is for the investigative part, for driving around and finding a place. And then I think at the time what we did is we got Andrew to hire me a DD, and I had a student come by to interpret, and we drove around and we told the guy, go here, go there. I had a map, and I randomly looked at a map and tried to figure out where I thought it might be dark. And most of the times I was wrong. Today, hopefully we could do better.
Yeah.
Get the DKU drone club to fly high at night. Figure out, where does it look dark?
A drone club. Does he have drones?
I assume somebody at DKU has a drone.
We have a drone club. We actually have a drone club.
See?
Really?
We do.
Wait, where does he get money for like drones? Like, I'm not sure.
There's a drone, right? There are many drones, but there's one belonging to DKU. Yeah, see, there's a drone club. So that's the way to fly it dark at night and take pictures, and we'll see where it's dark.
Okay, Gaurav, that would be your next task. I kind of feel like you know drone club better than I do.
Hey, you see, I got connections. Excellent. All right, guys.
Yep.
So,
Thank you so much, Professor.
Thanks for hanging out. Thanks for coming by. Sorry about going long and confused and sort of obscure, but I tried to do what I could to bring it down. And I really think it's a cool story. So it's for those who read Chinese, by the way, Yao wrote a book about it, and which is exists in English. It's not the best book on the subject, but it is the only one that was originally written in Chinese. Brian wrote a book on the topic, which is dated, it's old, but Brian's first book was about the story of this mirror symmetry story, so it's fun. There are many other popular descriptions, so you can find them. It was a cool game, meeting mathematicians. All right.
Yep. See you later.
Thanks for coming by. Talk to you soon. Have a great summer. Bye.
Bye.
This was recorded, so I'll send you the link, Aya, and you can distribute.
Sure, and I'll post it on YouTube.
Absolutely. All right. See ya.